Here we have to prove that the union of countable set is countable. I am denoting the countable set as En. So there have E1, E2, etc. En countable sets. We have to prove that the union of the countable set, union of En, I am denoting it as S, it is also countable. Okay. Do you know what is mean by a countable set? Here I given a 4 countable set. When we can count the number of elements in the set, then it is called as countable. Look, here E1 is a countable set. Why? Because we can count the elements in the set like 1, 2, 3, 4. And what about the E2? We can count the elements in the E2 like 1, 2, 3, 4, 5, 6. Similarly, we can count the elements in E3 and E4. So, E1, E2, E3, E4, etc., En, all are countable sets. Okay. Do you know how Rudin explains it? Rudin explains in some more mathematical way. I will show you by an example. Look here. We have a set A with elements x1, x2, x3, etc., etc. Okay, etc. We can say this is countable when we can count the elements in it like 1, 2, 3, 4, right? Means we can map an x1 to 1, x2 to 2, the third element of the set to 3, fourth element of the set to 4. Means we can find a function such a way that the first element mapped to 1, second element mapped to 2, third element mapped to 3. Okay, means there is a 1-1 correspondence between our set and the positive integers, right? Set of all positive integers. Rudin given a symbol like J to the set of all positive integers. So there have a 1-1 correspondence between the set of all elements and the J. Here look, if we define a function like f of xi equal to I, then what is f of x1? F of x1 equal to 1. What is f of x2? F of x2 to 2. So there is a 1-1 correspondence between these two sets, right? This is the way that Rudin explains a set is countable. Means we can find a 1-1 correspondence between the set and the set of all positive integers. In similar way, if we define f of x equal to 2x, where x belongs to J, the set of all positive integers, what is f of x1? F of x1 become 2 into 1 become 2. And what is f of x2? 4. What is f of x3? 6. 2, 4, 6, 8 and so on. It becomes our set E1. So our set E1 is countable. Okay. And what about 4, 8, 12, 16, our set E2? When we define a f of x like f of x equal to 4x, where x belongs to J, the set of all positive integers, then our E2 is also countable. Similarly, E3, E4 is also countable. We have to prove that the union of this countable set is countable, right? Now I am defining a sequence in such a way that in sequence the first element come 2. Then look to the next arrow. It contains the second element of the E1 and the first element of E2, right? 4, 4. The second element of the sequence is 4, 4. The first element is 2. And the third element of the sequence contain this third arrow, means 6, 8, 6. Okay, this is the third element. And what is the fourth element? The fourth arrow shows the fourth element, 8, 12, 12, 8. This is our fourth element. In similar way, we can find many elements. Okay, many elements in the sequence. What is the property of the sequence? This sequence contains all the elements of the En, right? All the elements of E1, all the elements of E2, all the elements of E3, etc., all the elements of En. These contain all the elements of the union of E, right? When we can find a 1-1 correspondence between our J and this sequence S, then we can say that S is countable, right? When we can count like 1, 2, 3, 4, then it is countable, right? But we can find a 1-1 correspondence between the subset of J. Here we can write this T 2, 4, 6, 8, 10, 12. The multiple of 2 is a subset of the J, right? This has a function. This has a 1-1 correspondence between our set S. we can do it by an exercise. You can do it as an exercise. We can map 2 to 2, 4 to 4, 4, 6 to 6, 8, 6, 8 to 8, 12, 12, 8. We can find a function in such a way. Okay. When we can find a subset of J has a 1-1 correspondence between with our S, then we can say that it is at most countable. It is not countable, it is at most countable. Do you know why? If this is finite, then we can't say that these two are isomorphic, right? If these two are isomorphic, then we can, if J and T and isomorphic, and we know T and S are isomorphic, then what we can say? J and S are isomorphic, so S and J is countable, so S is countable. But we can't say that J and T are equivalent. So to prove this is equivalent, we have to show that our T, means our this set, is infinite. How we can show that? To show T is infinite, it is only need to show that the S is infinite. If S is infinite, T become infinite. When T become infinite, means this T and J are equivalent. Do you know why? Let's look an example. I am giving 1, 2, 3. Okay, this is finite, and here 1, 2, 3, 4. Here had 2 and 4. If we thus we can find a 1-1 correspondence between them. No, never we can find a 1-1 correspondence. Our two elements are left in here. If it is infinite, then we can find a 1-1 correspondence between them, like f of x equal to 2x. If we define a function like that, then we can find a 1-1 correspondence between the elements of this set to this set, right? If they both are infinite, then these two elements are equivalent, right? Then these two sets are equivalent. So we can find only, if the S is infinite, then we can find only T is infinite, then T and J are isomorphic or equivalent, then our S is also countable. I hope you understand what I am saying. We need to find that S is countable. We get from here that S is at most countable. To show that S is countable, we have to show that the S is infinite. If the S is infinite, our T become infinite, then the J and T become equivalent. Okay, J and T become equivalent. So T and S are equivalent, J and T are equivalent. It means J and S are equivalent. To show that J and S are equivalent, we need to show that S is infinite. We know that our S is constructed by the union of En. Each En are infinite because each En are countable. Okay, each En are countable, so each En are infinite, and our S is made from this En, so our S is also infinite. So S is infinite means our T is also infinite. So there is a 1-1 correspondence between J and T. So J is equivalent to S. So our S is also countable. I will repeat it one more time to understand. This is really an example. We have to show that the union of countable set is countable. To show that, I am taking some E1, E2, etc. En, the countable set, and we have to show that our union of the countable set is countable. So for an example, I am taking the multiple of 2, multiple of 4, multiple of 3, multiple of 6, multiple of 8 as E1, E2, E3, E4, etc. En, and I am taking the sequence in the way like the arrow, in the way of the arrow. Okay, the first sequence become the elements in the first arrow, second sequence from the second arrow, third element of the sequence from the third arrow, and so on. If we can find a 1-1 correspondence between the subset of the J to our S, then we can say that it is at most countable. We can say that it is countable only if our S is infinite. We know that our S is made with the elements of E. is all are countable, so it is all are infinite. So our S is infinite, means S the T is equivalent to S. T is also infinite, means our J and T are equivalent, means J and S are equivalent. If J and S are equivalent, we can find a 1-1 correspondence between them, then our S is also countable.